In this video, we will review a variety of parent functions that you should be familiar with at this point. And as we go through each one, we'll talk about the key characteristics. Okay, so y equals x squared. By now, you should have learned that this is a parabola, so it's going to just basically do this type of deal. And I'm not being super careful with making sure this actually hits the right marks. I'm just looking for the general shape. So you should memorize and automatically know when you see y equals x squared, your brain should go, oh, that's a parabola. It makes this type of shape. Now, with that in mind, you should be able to talk about the domain, range, etc. Remember that the domain is the x values that are covered by a graph. In other words, how far it goes to the left and how far it goes to the right. Because this graph goes to the left forever and it goes to the right forever, then that is negative infinity to positive infinity. The range is the y values covered by the graph. So you can see that this graph, from bottom to top, it goes from 0 to positive infinity. All right, it has a low of 0 and it goes up forever. So that's why the range is going to be from 0 to infinity. We're going to go ahead and make the square bracket as we do the interval notation. The square bracket shows that 0 itself is included in the range. All right, in other words, this parabola touches 0. It's not an asymptote. There's nothing strange happens. It touches 0. All right, the zeros of the graph are going to be the places where the graph touches the x-axis. In fact, let's just say x-intercepts and y-intercepts. This will be more clear. So the x-intercept and the y-intercept are the same because you can see that the function touches the x-axis and the y-axis at 0, 0. So the x-intercept is 0, 0, and the y-intercept is also 0, 0. All right, now let's talk about decreasing and increasing intervals. Please understand that when we talk about decreasing and increasing, we are talking about x values. So whatever I say next, you should be looking at the x-axis. Now, if I were to go on a journey traveling this path from left to right, so for part of the journey, I would be going downhill, down, 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 down. All right, and then for part of the journey, I would be going uphill. Okay, so for the red part of the graph, that is decreasing, and the green part of the graph is increasing. Now, however, remember we're talking about x values. So the red part of the graph is this part of the graph if you just look at the x-axis, and the green part of the graph was the green part of the graph is from here to here. So this is where my intervals of decreasing and increasing are going to come from. Okay, so it's going to be decreasing from negative infinity to 0. All right, it's going to be decreasing from negative infinity to 0, and it's going to be increasing from 0 to positive infinity. Notice that we use round parentheses at 0. Notice that 0 is included in decreasing. It's included in increasing. Now, you can't be increasing and decreasing at the same time. So the idea is right at 0, you're neither increasing nor decreasing. So using parentheses means that 0 is not actually included in the set, in the interval. All right, now for symmetry, we have even symmetry and we have odd symmetry. Even symmetry is when the y-axis acts like a line of symmetry. If the y-axis splits this thing down the middle, then it's going to have even symmetry. So hopefully you can see that the y-axis does split this image perfectly down the middle. The y-axis is a line of symmetry. So that makes this even symmetry. Odd symmetry is rotational symmetry. So if you could turn a picture upside down and it still looked the same, that would be odd symmetry. All right, it's rotational symmetry around the origin. Okay, end behavior. So end behavior goes like this. As x approaches positive infinity, f of x approaches, well, maybe I'll just put it up here. As x approaches infinity, f of x approaches infinity. All right, that is 1/2 of the end behavior. This means as we go to the right, all right, as x approaches infinity, the graph goes up. As we go to the left, the graph goes up as well. So that's why we will say as x approaches negative infinity, f of x approaches positive infinity as well. All right, so that is our first function, the quadratic function, y equals x squared. All right, let's move on to the next function, the cubic function. Okay, now the cubic function, I'm going to change colors. The basic look of a cubic function is like this. All right, now I haven't drawn that perfectly, but that gives you the idea. That should be enough for us to talk about the domain. Remember, the domain is the x values. It goes left forever and it goes right forever. So the domain is going to be negative infinity to positive infinity. The range is the y values, all right, from least to greatest, from bottom to top. This graph goes down forever and it goes up forever. So the range will also be negative infinity to positive infinity. All right, now you should memorize this. Memorize the basic look of y equals x to the third power. You should be able to do a rough sketch just like I did, just from memory. All right, the x-intercepts and the y-intercepts. Again, this graph crosses the x-axis and the y-axis at the same point, 0, 0. So the x-intercept will be 0, 0, and the y-intercept will be 0, 0. Now, increasing and decreasing intervals. Well, as I travel from left to right, for this part of the graph, I am increasing. And then for this part of the graph, I'm still increasing. So the entire graph is increasing. Okay, so in terms of the x values, that is negative infinity to positive infinity. In other words, the entire domain is increasing. So it's increasing from negative infinity to positive infinity. All right, for decreasing, we can just say not applicable or something like that. Symmetry. This has that rotational symmetry I was talking about. I don't know if I can rotate this ink or not. I'm going to try. Okay, rotational symmetry means if I turn this upside down, it will still basically look the same. All right, so I'm going to rotate this 90 degrees twice. So there I rotated 90 degrees, and I rotated another 90 degrees. Okay, now because I didn't have it drawn perfectly, it doesn't appear to be at the origin anymore, so I'm just going to cheat a little bit. But you can see I turned it upside down, and it still basically looks the same. If I had drawn it perfectly, it would look exactly the same once I turned it upside down. So that gives it odd symmetry. All right, odd symmetry is this rotational symmetry. Now, end behavior. As x approaches negative infinity, meaning as we go to the left, f of x approaches. All right, so what happens as we go to the left? As we go to the left, the function falls down. So as we go to the left, the function approaches negative infinity. What about as we go to the right? As x approaches positive infinity, what does the function do? Well, as we go to the right, the function goes up. So that's positive infinity. All right, so that is the breakdown of the cubic function, y equals x to the third power. Let's look at the next function, the square root function. All right, the square root function has the following basic shape to it. It's sort of half of a sideways parabola. It's going to be something like this. Memorize that, all right? The square root of x starts at the origin and does half of a sideways parabola. Memorize that sketch. All right, now we can talk about the domain and the range. Remember that the domain is the x values. So the x values would be like this. All right, because the graph starts here and it goes to the right. So that's going to be from 0 to infinity. So the domain will be 0 to infinity. The range is the y values. The y values go like this, because the graph starts at 0 and it goes up from there. So the range is going to be also 0 to infinity. Notice we're using the square bracket because the graph touches 0. 0 is included. All right, speaking of touching 0, that's going to be the x-intercept and the y-intercept again. 0, 0, and 0, 0. That's where the graph touches the x-axis and the y-axis both. Okay, let's talk about increasing and decreasing intervals. Well, as we go from left to right, the graph is, hold on, I keep meaning to grab a highlighter. The graph is going uphill the entire way. So the entire domain, the graph is increasing. All right, now of course that domain is from 0 to infinity. All right, so increasing from 0 to infinity. No part of the graph is decreasing. It's going uphill the entire time. So this is not applicable. Okay, now in terms of symmetry, this has neither even nor odd symmetry. Remember, even symmetry is like this. If the y-axis is like a mirror, that would be even symmetry. Odd symmetry is like this, where if I rotated this picture around the origin, it would still look the same. This has neither of those qualities. So maybe I will just put nothing here, not applicable. End behavior. I'm only going to mention the right end behavior as x approaches positive infinity because the graph does not go to the left, all right? It only goes to the right. So I'm going to say for my end behavior, as x approaches positive infinity, okay, what happens to the function? Does it go up or does it go down? Well, as we go to the right, the function goes up. So that is positive infinity, but that was supposed to be an arrow. F of x approaches positive infinity. All right, so that is it for the square root parent function. All right, now it is time for cosine. Now, cosine is one of our periodic functions that repeats itself over and over again to the left and to the right. One cycle of the cosine function has a length of 2 pi, a period of 2 pi. So this is going to be 2 pi, which makes this pi. And this would be negative pi. And this will be negative 2 pi. Let's see. I'm going to go ahead and let this be 1. All right, so this would be like 0.5. And I will let this be a y value of negative 1. So you should memorize the following. Cosine starts at 1, all right? And then what happens is it falls to the midline, and then when it's halfway through the period, it drops down to negative 1, and then it comes back to the midline, and then finally it ends back where it started, all right, back at 1. So this is what one period of the cosine function looks like. All right, I'm going to show another period of the cosine function going to the left, but you'll see that it does the same pattern. So it falls to the midline, and then it goes to negative 1, and then it goes back to the midline and ends up back at positive 1. All right, so here is another period of the cosine function. So memorize that that is how the cosine function works. And it would keep on doing this forever and ever, okay? It would just keep on repeating this process. So just imagine that this keeps going up and down forever. Okay, now we can start talking about the domain and range and the rest of it. Okay, so cosine. So the domain is how far the graph goes from left to right. It's the x values. Well, this graph continues forever to the left and to the right. So the domain is still going to be negative infinity to positive infinity. Now the range is the y values though. This graph has a low and it has a high. It has a lower limit and it has an upper limit. It always stays between negative 1 and positive 1. So when it comes to the y values, that is the range. Negative 1 to positive 1. Notice we are using the square brackets to show that the graph touches negative 1 and positive 1. All right, OCD demands that I do this in blue. Aha! Negative 1 to positive 1. Okay, let's talk about the X-Intercepts. Well, the X-Intercepts, all right, there's one here, for example. If this is pi, then I have my first X-intercept at pi over 2. I feel like I got to zoom back in. So notice if this is pi right here, then that means that this is pi over 2. So that's my first X-intercept. Okay, now my next X-intercept is here. Now, what matters is how far apart are these? Is this a full period, which would be 2 pi, or is this half of a period? Well, let's count the tick marks. Notice that pi is 1, 2, 3, 4 tick marks. All right, 4 tick marks is pi. Now, let's count how far apart these x-intercepts are. 1, 2, 3, 4. So, from here to here, these are pi apart. All right, in other words, to get to the next x-intercept, I would have to add pi. So, one way that I can describe the x-intercepts, I can start with pi over 2, and then I'm going to, so that would be one x-intercept right there. But I want to somehow capture all of the x-intercepts. Now, if I added pi, that would give me another x-intercept. Or if I added another pi, that would give me another x-intercept. So adding multiples of pi, that would be pi n. All right, I'm just using n to represent 1 pi, 2 pi, 3 pi. So in this way, I can capture all of the x-intercepts. But x-intercepts are always the x value, comma, 0. So this expression represents all of the x-intercepts. What about the ones to the left? What about negative pi over 2 and the rest? Well, just understand this. N could be -1 or 0 or -2. So by letting n be any natural number, it automatically covers the x-intercepts to the left as well. So we really did get all of the x-intercepts. Are there infinitely many y-intercepts as well? Nope, there's just the one, all right? Right here at the very top, that is 0, 1. That is the only y-intercept. Okay, now this graph has many increasing and decreasing intervals, and that's really beyond the scope of what we want to do. So I'm just going to leave this blank. We're just not going to deal with it. Obviously, this goes forever and ever, and for example, this would be a decreasing interval, and then followed by an increasing interval. And so we're just going to have decreasing, increasing forever and ever. But that's so awkward that it's just not worth doing. We can easily talk about symmetry, though. All right, this has even symmetry. Remember, even symmetry is the one where the y-axis is a line of symmetry. And notice that the green and the blue are mirror images of each other using the y-axis as the axis of symmetry. So this is even symmetry. Okay, end behavior, we can't really talk about end behavior either because it doesn't just go in one direction. It goes up and down and up and down and up and down forever. So there is no end behavior that we can nail down. I just want to add in right here that n is a natural number. All right, that really should be part of our description. Okay, let's move on to the exponential function e to the x power. So we picked e to the x power. E is approximately 2.72, but that doesn't really matter. The exponential sketch is going to look the same for any number that's bigger than 1. All right, and the basic sketch is going to be like this. It's going to pass through the point 0, 1. It's going to treat the x-axis as an asymptote, and it's going to be increasing. So it's going to look something like this. Okay, it got a little bit steep there. All right, let me try that again. Okay, this is the idea. Now, of course, it appears to touch the x-axis as I'm going to the left, but this is an asymptote. So in your mind, just understand that what's actually happening is I'm getting closer and closer to the x-axis, but I'm never touching it. So please memorize that that's what the sketch looks like for an exponential function like this. All right, now the domain is going to be from negative infinity to positive infinity because it goes to the left forever and it goes to the right forever. Now the range is the y values. Does this go down forever and up forever? No. This has a floor to it. This graph does not go below this line. All right, this is an asymptote. It does not go below here. So the x-axis has a y value of 0. So this graph stays above 0 the entire time. So from bottom to top, I'm going to say 0 to infinity. All right. Okay, this is supposed to be red. I'm going to say 0 to infinity. Now, if you're saying, well, wait a minute, I thought you said it doesn't touch the x-axis, so how are we saying 0? Well, that's why I'm going to put a round parenthesis on here instead of a square bracket to show that it doesn't actually touch 0. So this means 0 is not included. Infinity always gets the round parenthesis. X-intercepts, of course, there will be none. There are no x-intercepts. Because the x-axis is an asymptote. All right, what about the y-intercept? Yes, it touches the y-axis right here at 0, 1. So 0, 1. Decreasing and increasing. Well, as I go from left to right, this part of the graph is increasing. Notice I'm going uphill. Oh man, that's the entire graph. So the entire graph, the entire domain is increasing. Okay, so that's going to be from negative infinity to positive infinity, it's increasing the entire way. So there are no decreasing intervals. So I'll just put not applicable. All right, what about symmetry? This doesn't have either kind of symmetry. It's not even, it's not odd. The y-axis is not a line of symmetry, and this will not look the same if I rotate it around the origin. So symmetry, there is none. Okay, maybe I'll just say none for all of these things where I've been saying not applicable. I think I'll say none. All right, just to be consistent. End behavior. Okay, what happens as we go to the left, right? What happens as x approaches negative infinity? All right, as we go to the left, the graph gets closer and closer to the x-axis. All right, it gets closer and closer to 0. All right, that asymptote. What happens as we go to the right? What happens as x approaches positive infinity? Okay, well, as we go to the right, the graph goes up into the sky. So as x approaches positive infinity, f of x approaches infinity. All right, so that is it for the exponential function, e to the x power. Okay, Now, the logarithmic function, natural log of x, is going to be, it's the inverse of this. So just imagine taking this graph and reflecting it over the line y equals x. All right, that's basically what's about to happen. If I reflected this over the line y equals x, I'm going to get a graph that looks like this. Okay, so watch for this green shape to be happening when I do this graph below. All right, and memorize this. So in my last graph, the exponential graph, the graph passed through 0, 1. Well, this graph is going to pass through 1, 0. So that's a key point that we need to make sure that we hit. Other than that, the y-axis is going to be an asymptote. All right, it's going to be a little bit tricky for me to draw, but I will try. Okay, this is the basic idea. Memorize the look of this logarithmic graph. Y equals natural log of x. Okay, now we can talk about the stuff. The domain. All right, this is the first graph that we've had so far that does not go left and right forever. It hits a brick wall here at the y-axis. It does not go past that. And so the x value here is 0. So the domain is from 0 to infinity. All right, it only goes from the y-axis over to the right. We're going to use parentheses to show that it doesn't touch the y-axis. It's an asymptote. The range, that's y values. This graph goes down forever and up forever. So the range will be from negative infinity to positive infinity. X-intercepts. Yes, the graph touches the x-axis right here at 1, 0. 1, 0. Y-intercept. Nope, the y-axis is an asymptote, so it's not going to touch the y-axis at all. So I'll just say none. Decreasing and increasing intervals. Well, this entire graph is increasing. It's going uphill the entire way. So the entire domain, notice that, remember, the domain is from 0 to infinity. Okay, so when we do these increasing and decreasing intervals, we can't go past the domain itself. So this is going to be increasing from 0 to infinity, which is the entire domain. Decreasing, it's never decreasing. There are no decreasing intervals, so I'm just going to say none. This has no type of symmetry. The y-axis does not split it down the middle. It doesn't look the same when I rotate it upside down around the origin. So it has neither symmetry. End behavior. Okay, let's talk about the end behavior as x approaches negative infinity. What happens as we go to the left? Well, actually, I need to be careful because normally I say as x approaches negative infinity. But we have an asymptote here, people, so x does not approach negative infinity. The graph on the left side of the graph, it approaches 0. All right, it's getting closer and closer. The x values are getting closer and closer to 0. So instead of saying as x approaches negative infinity, we have to say as x approaches 0. Okay, so what happens to the function as we go to the left, as x values get closer and closer to 0? Well, as we go to the left, the function falls downward. So as we get closer and closer to 0, the function approaches negative infinity. Now, on the right-hand side, it works more normally. So as x approaches positive infinity, what happens? So as we go to the right, the graph goes up. So that's going to be positive infinity. Okay, who's up next? The sine function. All right, the sine function is another periodic function, which means it's going to repeat itself forever as we go to left and right. So just like the cosine function, the sine function has a general look that goes like, I'm going to have to do a better job of drawing it, but it's going to go up and down forever to the left and to the right. Now, I've zoomed in so I could write these tiny numbers here. The sine function begins to repeat itself after going pi units. After going 2 pi units. So that is the period of the sine function. So I'm going to start off by drawing one cycle of the sine function going to the right. Now, unlike the cosine function, which started off up high at 1, the sine function starts at 0. Now, at the first quarter of a period, it rises up to its highest point of 1, and then it falls back to the midline, and then it goes down to its lowest point of -1, and then it goes back to the midline. So one cycle of the sine function is going to look something like this. Okay, and then it would continue on like that forever. Now let's do another cycle of the sine function going in the opposite direction. So we see that it's falling. Now it would continue to fall down to its lowest point, and then it would rise back to the midline, and then it would hit its highest point, and then it would fall back to the midline. So as we go to the left, one cycle of the sine function would look like this. And then that would continue forever. Okay, so here is what 2 cycles of the sine function would look like, and it would just keep going up and down forever in both directions. So that should give us enough of a basic sketch that we can go ahead and fill in the key information. So the domain is going to be -infinity to positive infinity because of the way it goes to the left and to the right forever. The range. This graph has a low of -1 and a high of +1. So that's the range, -1 to +1. I'm using the square brackets to show that the graph touches -1 and +1. They're included in the range. X-intercepts. This graph has multiple x-intercepts. The first x-intercept is right here at 0. Okay, so if I were making a list, I might say 0, 0. But I really want to have one expression that captures all of the x-intercepts. So let me leave a little bit of space here to add some stuff. All right, so fine. The first x-intercept is right here. The next x-intercept is here. Notice that these are pi apart. And look, the next x-intercept would be here. That's another 4 tick marks. That's another pi. So every time I add pi, I'm going to get another x-intercept. Okay, so if I did 0, but then if I added pi, if I added 1 pi, or 2 pi, or 3 pi, so I'm going to say n pi to show that I'm talking about multiples of pi, any multiple of pi. Okay, comma 0. Now, if I let n be an integer, n is an integer. Okay, that means 0, 1, 2, 3, 4, also -1, -2, -3, -4. And in fact, that's how we capture the x-intercepts going to the left, because n is allowed to be -1, -2, etc. 0 plus anything, like you know how 0 plus 5 is 5? 0 plus n pi is just n pi. So I don't really need the 0 plus part of this. So I will just tidy it up and write it like that. The y-intercept, it hits the y-axis only at one point, 0, 0. All right, just like we said when we did cosine, we're just going to skip over the decreasing and increasing intervals. This will have many, many increasing intervals that repeat over and over again. It has an infinite number of decreasing intervals, but that's just not worth getting into. Symmetry, we will talk about symmetry. This is going to have odd symmetry. Remember, odd symmetry is the one where it's rotational symmetry. If the graph looks the same, right? Here's like a little sketch of something that would have odd symmetry. If I turn this upside down, it would still look like this. That's what odd symmetry is like. Whoops. Now, why does this have odd symmetry? You can see it best if you just focus on, for example, this portion of the graph right here. Imagine that I turn the entire graph upside down. This little yellow part, if I turn that upside down, it's still going to have the same shape. Well, that really goes for the entire graph. If I turn the entire graph upside down, it would actually look exactly the same. All right, so that is going to be odd symmetry. And this has no end behavior that we can nail down. As we go to the left forever or to the right forever, it just goes up and down and up and down. So there's no end behavior we can really describe. All right, so that is it for the sine function. Let's move on. All right, let's talk about rational functions. This is the parent function of rational functions, y equals 1 over x. Now, this is interesting because the x-axis and the y-axis are both asymptotes. So what happens is we're going to have one branch of this function in this quadrant, sort of going like this. Okay, this is really hard to draw. One more try. Maybe if I go in this direction. All right, so we'll have one branch going like this, asymptote, asymptote. And we'll have another branch in this quadrant. Okay, this gets so close to these asymptotes that really makes it tricky to draw. Okay, this is the basic idea. The y-axis is an asymptote. The x-axis is also an asymptote of this guy. All right, so the domain. We're going to have to split this domain up into two parts because the domain is really all x values except for 0. So the domain, the part of the domain that comes from the left side is going to be from -infinity to 0. All right, use parentheses to show that 0 is not included in this. It's an asymptote. And then we'll say union 0 to positive infinity. Now that represents the x values of the right-hand side. So it's really every x value except for we had to leave out 0. 0 is never touched. And we're going to have to do the same thing for the range. This graph covers all y values except it skips over a y value of 0, all right, because that's an asymptote. So the range is going to be the exact same thing. -infinity to 0, all right, that's this first branch down here, union 0 to infinity. All right, that's the y values of this branch over here. Okay, x-intercepts, there are none because the x-axis is an asymptote, all right? It doesn't touch. Y-intercepts, there are none. Same reason, doesn't touch the y-axis. It's an asymptote. Decreasing intervals. Okay, so from left to right, this part of the graph is decreasing. And from left to right, this part of the graph, see how I'm going downhill? So, I mean, I had to jump up here and then go down, but I have two intervals that are both decreasing. So, for increasing, I'm going to say nothing. I'm going to be oddly mute. But for decreasing, it's decreasing over the entire domain. So, it's going to be negative infinity to 0, union 0 to infinity. The whole thing is decreasing. Increasing, none. There are no increasing intervals. Symmetry. This has the odd symmetry. If I turn this picture upside down, it's still going to look the same. So that gives it odd symmetry. It's the rotational symmetry. Okay, and behavior. As x approaches negative infinity. All right, so what happens to the value of the function as we go to the left? Well, as we go to the left, the function gets closer and closer to 0. So that's going to be the end behavior on the left side. All right, what about, what about as x approaches positive infinity? What happens as we go to the right? Right? What happens to the value of the function? Well, as we go to the right, again, the function gets closer and closer to 0. So that's going to be the end behavior on the right. All right, what's next? Oh, the tangent function. All right, now I'm about to graph the tangent function. I had to zoom way in because there's a lot of detail to it. Tangent function is another periodic function which repeats itself over and over again forever as we go to the left and to the right. But this graph has asymptotes in it. So the one period of the tangent function is only pi. Okay, so the period is pi. It repeats itself after one of these. And what I always like to say is the tangent function begins and ends on the x-axis. And right in the middle, there is an asymptote, right between these 2 points. So normally I use a dotted line as an asymptote, but OneNote does not allow you to, there are no dotted lines in OneNote. So instead, I'm going to use this turquoise line. All right, pretend this is a dotted line though. Okay, maybe I can make it a little bit thinner. Okay, that is my asymptote. Now, before I draw the thing, I think I'm just going to do that aspect of it over and over again. So, the tangent function begins and ends on the x-axis with an asymptote in the middle. And then that repeats. So if I go another pi, if I go to 2 pi, I'm going to touch the x-axis again. If I go, every time I go pi, it's going to be another x-intercept. All right? Now, in between each of these patterns, in between each of these purple dots is going to be an asymptote. Now, I wonder if it would be easier for me just to cut and paste this because they're slightly tricky to draw. Okay, so there's an asymptote. All right, here's another asymptote. All right. All right, and one more asymptote. Okay. This probably was not the most efficient way to do this, but what are you going to do? All right. So now I'm ready to draw. All right, let me zoom in again. All right, so the tangent function is always increasing. So I'm going to approach this asymptote, but it needs to be increasing. So it's going to be doing something like this. All right. And on this side of the graph, I'll just keep this more or less in the middle. On this side of the graph, it had to approach the asymptote. All right, of course, at some point it's going to pass through this intercept, and it's going to approach the other asymptote. All right, and it's going to do the same thing right here. And as I go to the left, I'm going to see the same pattern. All right, notice from left to right, these are all increasing. Increasing. All right, so this is basically what the tangent function looks like, repeated over and over and over again. Maybe I'll put some just dotted lines to show that that's just going to continue on forever. Okay, time to zoom out and talk about this. All right, so when we talk about the domain, really the domain, we have all these asymptotes that we have to skip over. So we're going to have to come up with a clever way of talking about the domain. Basically, the way we're going to get around it is, fine, we're going to admit that the tangent function goes left and right forever. So that would tempt us to say that the domain is going to be negative infinity to positive infinity. All right? Except at the last second, we're going to step in and we're going to say, all right, except for all of these asymptotes. So let's talk about where the asymptotes are, so we can say, well, except not that. We're going to leave out the asymptotes. All right, so look, the first asymptote, here, I'll just use this pen. The first asymptote is right here. Notice that this would be pi over 2. So we're going to say x cannot equal pi over 2. All right, x can't equal pi over 2. But then, what about all the other asymptotes? How far apart are these asymptotes? Count the marks. 1, 2, 3, 4. These are 4 marks apart. Hopefully you can see that that is pi. All right, don't believe me? How many marks does it take to get from 0 to pi? 1, 2, 3, 4. So 4 marks apart, that's pi. So if I were to take pi over 2 and add pi, that would take me to the next asymptote. What if I were to add 2 pi? That would take me to the next asymptote. So if I want to get all of the asymptotes, I would say plus n pi. All right, because that will be any multiple of pi. That will hit all of the asymptotes. And if we say that n is an integer, that gets all of the asymptotes going to the left as well, because integers can be negative numbers like -1, -2, -3. All right, so the domain is negative infinity to positive infinity, except it can't be any of the asymptotes. That's basically what we just did. All right, it feels like cheating. But the range is back to normal. The range is the y values, and it goes down forever and up forever with no gaps in between. So the range is negative infinity to positive infinity. Okay, let's talk about the x-intercepts. Well, it's going to be real similar to how we were just talking about the asymptotes. The first one is at 0. Okay, so let's start with 0, but then we're going to have another one at pi, and another one at 2 pi and 3 pi. All right, so we could say that we're going to have these x-intercepts at 0 plus n pi, comma 0. And of course, we don't really need the 0 in front. 0 plus anything is that thing. Okay, and remember, n is an integer. So that captures all of the x-intercepts, even the ones that are negative. Okay, what about y-intercepts? Yes, there's one y-intercept, and that is 0, 0. Okay, now, increasing, decreasing, this thing is increasing forever. Every one of these branches is increasing. All right, it's all increasing. So for decreasing, we're just going to say none. Now for increasing, now remember we're talking about x values here. Since the entire graph is increasing, that is the entire domain. So guess what? We can just copy what we said for the domain. The entire domain is increasing. So let's just duplicate that. Boom, the domain. How about symmetry? Well, it'll be easiest to see if you look at just this inner branch, the middle branch here. Can you see that this has the odd symmetry? If we turn this upside down, if we rotate it, it would still look the same. That's odd symmetry, but it applies to the whole picture. So this is going to be odd symmetry. All right, and of course we can't talk about end behavior when we're doing a periodic function because it just repeats over and over again. It doesn't approach any particular value. All right, what is next? We've got to be getting towards the end of our journey. This video is getting very long. How many? Oh, is this the last one? All right, last one. Memorize this. The absolute value function, y equals the absolute value of x, forms a v. All right, so it's going to be like this. All right, hold on. I think I'll cheat and use my line drawing tool. All right, now if we really do it perfectly, this should be like a 45-degree angle. All right, and you know what, now that I think about it, I should make an arrow with it. Okay, now we're good. All right, so the absolute value function forms this V shape. All right, so the domain is the x values. This graph covers every x value from left to right from negative infinity to positive infinity. Now the range, that's the y values. This graph has a bottom to it. It doesn't go any lower than 0. So it goes from 0 and then it goes up from there. So that's 0 to infinity. That's the range. X-intercepts, well, the x-intercept and the y-intercept. The graph touches the x-axis and the y-axis at 0, 0. All right, decreasing and increasing. Well, from left to right, this graph goes downhill. That's decreasing. And then it goes uphill. That's increasing. But when we talk increasing and decreasing intervals, we really are talking about x values. So the decreasing part is this part of the graph. And the increasing part is this part of the graph. All right, so stare at the x-axis as you say these intervals. So this is from negative infinity to 0. So the decreasing interval, let me get rid of my highlighting. So negative infinity to 0, and then 0 to infinity. Okay, always use parentheses with increasing and decreasing intervals. The 0, the point where it changes from decreasing to increasing, is neither increasing nor decreasing. This definitely has even symmetry. See how the y-axis is an axis of symmetry? It splits it right down the middle. That makes this even symmetry. And behavior. What happens as x approaches negative infinity? In other words, what happens to the value of the function as we go to the left? Well, as we go to the left, the graph rises. So it approaches positive infinity. What happens as x approaches positive infinity? All right? In other words, what happens to the value of the function as we go to the right? As we go to the right, the graph rises. So that's positive infinity again. All right, and that's it. That was our last function. All right, I hope you've enjoyed our journey of exploring the parent functions that you should have memorized. Now just make sure you go back and memorize. You should be able to do the basic sketch of every one of these parent functions from memory. That was a lot of work we just did.